Dear all, good evening. In the last class, we have solved the bar element problem with the elimination approach. Okay, this is the last content. To get the information, you can refer the last video in my playlist. Now, let us see the similar problem from the penalty approach. Okay. Now, this is the one-dimensional bar element with help of the penalty approach. See here, this is the one element, bar element. This is 1 and this is 2. Element number 1 and element number 2. So here some point load is acting. So we are taken as some section. So that's why we are divided into element 1 and element 2. This is the node 1, node 2 and node 3. L1 and L2 are the lengths. Here they are given some length, some gap, that is called specified displacement. Okay, in the penalty approach you will get the new terminology. One is A, that is specified displacement. Other one is C, that is large stiffness. Okay, similar to the last problem, here also you have to find out the K1 and K2. So here the area and Young's modulus is same. So that's why here K1 and K2 same. As you know the formula A1 E1 by L1. Okay, here you know from the formula, after adding all the values like area, Young's modulus and length, you will get the K1 value and K2 value. Okay, then you have to add the all elemental stiffness values. Then you will get the capital K, that is a global stiffness matrix. So here K1 and K2. So here even though both are same, you have to give the different numbers 1 2 1 2. Here 2 3 2 3. Then after that you have to get the capital K value. As you know, first of all you have to write the 3 by 3 matrix because 1 2 3 3 nodes are there. So 1 2 3 1 2 3. So then you have to add here. See 1 by 1 1 by 1 33. Then 2 by 1 minus 33. Then 3 by 1 3 by 1. There is no 3 by 1 here. So 0. Then similarly 1 by 2 1 by 2 minus 33. Then 2 by 2 here and here is there. So plus 33 plus 33. This value. Then you will get the 66. Then similarly you have to follow the remaining values. This is similar to the last problem. Okay, then you have to write you have to combine all the values. Here 33 33 you will get 66. Then you have to write K11 K12 K13. You know 21 22 23 31 32 33. So here the new formula is, except C, you have to, for the last form you have to add the C values. Here C is the large stiffness. See here for K11 and K33. See here starting at the ending. These are the fixed supports. So you have to add C values at the starting and ending. Okay, then Q1 Q2 Q3. See KQF. Okay, F1 F2 F3. Here also at starting and ending fixed supports. So plus CA1 plus CA3. This is a new formula, CA1 CA3, right? So here if you observe this figure, this is the fixed support 1 and 3. So F1 and F3, and here F2 they are given some load. Here Ft is equal to P value, but here F1 F3 they are not given any loads, so 0 loads. Only F2 is given some load P. You have to write P value. Here 1 2 3. At third point A is there. So here A3 is equal to A. Here the first node at 1. So A1 there is no value, not given, that is 0. So A1 is 0 and A3 is some value. So after then you will get the direct matrix. So then you have to use this matrix to solve the Q1 Q2 Q3. Okay, here you can use the ES calculator to solve the matrices directly. So 3 by 3 matrix, you will get direct Q1 Q2 Q3 values. Okay, so then you have to find out the stress values. You can use the same formula from the elimination approach, that is Young's modulus into epsilon, sigma 1 and sigma 2. Similarly you have to find the stress values. Then reaction forces, here the formula is different. Here again 1 and 3 fixed supports. So you will get R1 and R3. So here the formula is minus C into Q1 minus A1 is the difference of the displacements, Q1 minus A1. Okay, then here also Q3 minus A3 at 1 at 3, so Q3 minus A3. But if you observe there is no A1 value, so you will get only minus CQ1. Here see, here if A3 is given, you will get this formula. Suppose if there is no A3, you will get this value. This is the formula. Let us see the problem. See here, this is the similar problem. Yes, close. Okay. From this problem, see, 150 mm, 150 mm, area is given, and Young's modulus is given, and P, load is given. Okay, load is given. Determine the displacement, stress, and support reactions. Okay, here also you have to find out the K1 value, K2 value, similar formula. Then you will get the capital K, as I told earlier. Okay, then you have to use the matrix KQF, as I told earlier, plus C, CA1, CA3. Here Ft is given, that is 60 kilonewtons. Then you have to use this equation. From this, see here, CA3, C into A3. Here C is maximum value. Here we observe, see this equation, see 66.66. Maximum K is a, here C is the large stiffness. Maximum K is a 10 power 4. Here 66.6 into 10 power 3 into 10 power 4. This is the 10 power 7 is the maximum K is, that is C value. Okay, so you have taken same value, 66.6 into 10 power. Okay, like that you will get the C value. Then A3, here A3 is given in the problem. See here, 1.2 mm. So here all the values here taken in meters. Here L2 you have to convert into meters, 0.15. A2 250 mm square, again you have to multiply with 10 power minus 6, you will get area. So like that you have to convert all the values into meters square, meters only. So here also you have to convert 1.2 mm into 1.2 10 power minus 3 meters, you will get the C value. This entire value is like that. Then you have to solve this equation. This is 3 by 3 by here 1 2 3 3 rows to 1 column. So if you cancel this 3, you will get the 3 by 1, that is 3 by 1. Okay, you can use the ES calculator. After adding 1 2 3 1 2 3 and these values, you will get the Q1 Q2 Q3, so direct values in meters. Okay, after that you can follow the similar procedure for the stress values as per the elimination approach. At the end you have to find the reaction forces. Here A1 is 0, so only CQ1, you know, C value and Q1. Similarly R3 value, C into Q3 minus A3, A3 is some value, here A3 in meters, and Q3 value, then you will get the R3 value. So like that you have to solve this type of problems. Okay, right, thank you.